I know you're having a good time chatting, but time's up. Thought I'd read the announcements. I know you've probably heard these through the week, but let me just mention one or two of them. Wisdom Wednesday will be tomorrow at 2:30 here in the museum, and it will feature Harold Bruner and Carolyn Carr, who will be talking about day hiking opportunities, so that might be of interest. Remember to do your course evaluations. Holiday Social is coming up December the 6th. They will probably still accept your registration unless they have filled up already. And I've had a couple of people ask me about the winter calendar or the winter catalog. According to the list, it will be available on January the 10th. So January the 10th, then you can call the office and find out what's going on. Okay, today, last session, and I have a lot of things I wanted to talk about, and I'll probably run through some of this fairly quickly. I thought about taking out some of the slides and all, but I think I'll leave a lot of them in there, and then even if we don't cover things in great detail, you'll have the pictures of the slides when I send you the link, and you can examine and then read up some more on what we've been talking about. But let me just recap briefly. We're looking at plate tectonics, movement of material from beneath the crust toward the crust, and the spreading of the surface here. Here's an example occurring at the Mid-Atlantic Ridge, pushing South America and Africa away from each other. And you have the uprising in these areas where the plates come together. Then you have the subduction, which creates faulting. Active faulting creates earthquakes. You have gases, magma escaping to the surface, volcanic action in high mountain ranges, part of the alpine system that we talked about last time. And so all havoc breaks loose at the point where these plates are coming together. Hence the localization of volcanoes, the ring of fire, all of those events that we talked about last time. Went on to describe the position of the ancient continents. Here is one phase after the breakup of Pangaea, Gondwana continents to the south, Phalarosia to the north, eventually spreading apart and forming the continents as we know them today. Talked a little bit last time about the history of North America, primarily about mountain building out west in the Rockies, and then the back and forth crunching here in the east that has created the Appalachian Mountains. At one time very high mountains, but since eroded and worn down by the repeated action of various events that occurred here. In this part of the world, just to illustrate, the fall line is a very significant dividing line. It's referred to as the fall line because of the waterfalls created as rivers flow from the hard rock areas, the metamorphic, the igneous material of the Appalachian system, the ridge and valley area, onto the coastal plain. But it's also an important dividing line if you look at the geologic history of this area. These areas within, to the north and to the west of the fall line are old remnants of the various mountain building periods that existed here. And there's several of these, and I just mentioned some of these at different periods where the continents have come together, backed off. The most recent then is the Allegheny Appalachian, which happened in the formation of the Pangaea about 325 million years ago. The areas to the south are much more recent. These are sedimentary beds. This generally referred to as the coastal plain. The rocks are softer and quite different in their characteristics from what you find in the Piedmont and the Appalachian system area. In general, if you were to draw a profile, this would be characteristic up through maybe the Virginia, Pennsylvania area. You have the crystalline or the basement rocks or the igneous material here from the various impact events of the continental collisions that occur. And then the sedimentary basins to the west wrinkled up into folded features here in the ridge and valley area just west of the Blue Ridge, and then eventually out into the various sedimentary layers that extend on further to the west. So this is basically the profile that exists here in the Appalachian system. I see that Mike Mason, my resident geologist, is back, and so after class I'll let you address all questions about this to him instead of to me. Okay, I wanted to move on and talk a little bit about earthquakes. And here's a recent map that's come out from the USGS showing the earthquake hazards. Now, we've talked about this last time, all of the crunching and the uplift. Remember the Farallon plate and all the things going on out west. So this would be an area where you would have active mountain building, and these earthquakes then would be associated with the active faulting occurring in those areas. One example would be the San Andreas Fault along the coast of California, which is a very active fault and creates earthquake events periodically. Another area of earthquakes has recently shown up here in the middle of the country, and this is in the area of North Texas, Oklahoma. This is all man-made. This is caused by drilling for oil and gas within these areas and the use of a particular technology called fracking, where they will inject wastewater into underground layers that will crack the rock and essentially replace the oil or force the oil out or the gas by the injection of water, and that's creating disturbances and cavities that eventually can lead to earthquakes. And some of them have been pretty significant. Here's one picture of one. Most of this in Oklahoma, so this is a new area of concern. Haven't heard so much about it in the last couple of years, but it is an area of significant seismic activity, again, induced by humans. Another major area of earthquake occurs in the middle of the country. Here in this area, you may have heard of the New Madrid fault zone. New Madrid is a small town in this area that was the epicenter of a major earthquake back in the early 19th century, and very strong, destroyed a lot of homes, created severe hardship within this area. They say reversed the course of the rivers within this region. Well, this is not an area where you would expect to find a lot of earthquakes. This is not at the contact point among these plates coming and bumping into each other. So what's going on here? The fact is they don't know exactly. There are several different ideas. Here it's still active, and so you can see earthquake events since 1974, so it's still active. Not the big one as occurred in the last century, or 2 centuries ago, I guess, but nevertheless still active. One idea is this notion of the real foot rift. The idea is that at one time here in North America, the continent was beginning to divide or making an effort. I'm not sure a continent can make an effort, but anyway, it was trying to split apart as Africa is doing today. Remember, in Africa, in East Africa, you have a rift valley where the continent is literally moving, 2 sides moving away from each other. Well, the idea here is that North America was in the process or started to divide, and then it stopped. And so this whole process came to a halt. But nevertheless, the remnants of this, sort of the leftovers of this, are still causing some disturbances here in the middle of the continent. It's referred to as the real foot rift. So it's an ancient rift that never really developed. Another idea is that, if you recall, the Farallon plate has come in from the Pacific Ocean, buried its way beneath North America, and it's possible that this has continued and is creating disturbance here in the middle part of the country, some sort of association. Then the third idea is that this is simply rebound from the last glacial event. The weight of the glaciers, the weight of the ice has gone, and so essentially the continent expands as a result of that. So, but the fact is, at least according to what I've read, there is no definitive solution or answer to why earthquakes are happening within this area. Another interesting area is over here in the east. Some associated with the Appalachian Mountains. These are just sort of leftover faults buried beneath the surface. Again, readjustment as a result of the breakup of Pangea many millions of years ago. And then similarly, again, without knowing exactly, right down along the coast of South Carolina, you may be familiar that there was a major earthquake in Charleston in 1886, destroyed a lot of buildings. And again, not knowing exactly what's happening here, but probably some leftover consequences of the breakup of Pangea. And so these are examples of intraplate earthquakes. So even though most earthquakes, most faulting is happening at the margin of the plates, you still get some of this activity within the plates themselves. So anyway, some interesting characteristics here. Okay, well, let's move on. I'll talk a little bit about islands and the various kinds of islands, because we're going to move on to looking at the oceans here for just a little bit. Islands come in many forms, many styles. Some of them are continental fragments. So these are just fragments of some of the ancient continents that have broken away and moved away from South America, and this whole area in Central South America is very complex in what has been happening here, and really not going to get into it too much. But that's Cuba, Hispaniola. These are fragments then of the ancient continents and have moved away and broken away and continue to drift away. There are more of these fragments around the world, so the islands of Indonesia, Sumatra, Java, Borneo, these are fragments of ancient continents. Here's another one. Madagascar was part of Gondwana, separated from Africa, and has now been moving off to the east, plowing into the Indian Ocean. So some islands in the world are just bits and pieces of these ancient continents that have moved away from the major continental crustal areas. Other areas are former shallow areas. And so if you look at the Bahamas here, these are features that are exposed portions of ancient seabed. And they are basically made up of limestone. And so the limestone has emerged here, and it's this oolitic limestone, basically bits and microscopic bits and pieces of shells and leftovers from sea creatures that has been rolled around by the action of the water and created little bits that look like eggs. And that's the origin of that word, refers to eggs. And so rocks then made up of this type of lime conglomerate or material, I guess, that's been processed in this fashion. And so these are quite common around the world. These shallow areas that are now exposed. Here's another one. Yucatan is essentially limestone, similarly part of a former shallow sea. If you go to the Yucatan, you see a lot of white rock. You see these typical sinkholes, cenotes. And so all of this is underlain by limestone, as is Florida and many other similar areas around the planet. Some islands are volcanoes. So here's Tenerife and the Canaries. Rod and I were just talking about the Canary Islands, pretty area. So these are volcanic features beneath the sea. Volcanic material comes to the surface at a plate boundary or a hot spot, which is something I'll talk about in a minute, and create volcanic features. And they are found all over the place. Diamond Head, Honolulu in Hawaii is an ancient volcano, not so ancient really. Martinique, volcanic island. You see island strings across the ocean, so the Aleutians, the Hawaiian Islands, these are formed by volcanoes. And several of these are created, well, let me see what I have next, Mariana. Several of these are created as a result of one plate dipping beneath the other. So the Mariana Islands would be an example of that. What you have here is a volcanic chain, which is the area beneath the zone where at this trench right here, you find the Pacific, portion of the Pacific Ocean moving to the west. And as it's dipping below another plate here in this region, it's not pushing up high mountains up into the air as the Andes or the Alps, but nevertheless the action is similar. It is creating the disturbance in this region that leads to volcanic activity. When the volcanoes break the surface, then that creates islands. So these are all, these chains of islands, in this case, are the result of this subduction of one plate beneath another in this part of the Western Pacific. So there you see the islands happening. This is a similar event in the Eastern Caribbean. So these Windward Islands are all formed in the same manner. You have plate off of the Atlantic Ocean dipping beneath, and as it does, it creates the venting of the gases and the magma coming to the surface and creating islands here in this part of the ocean. Another thing that occurs is what formed the islands of Hawaii. They are the result of what's called a hot spot. A hot spot is a location where, for some reason, this stuff comes bubbling toward the surface and the plate moves across it. And as it moves across it, that bubbling magma coming to the surface, then if it breaks the surface, will create islands. So if you look at the Hawaiian Islands, the islands are progressively older as you move to the west, this whole chain of islands. So these are much older. The big island of Hawaii over here to the east is the youngest of the island. In fact, it's being formed as we speak right now. And so the hot spot is right there. What's happened is the plate has moved from southeast to northwest, and as the plate, as the crust of the earth travels across this single hot spot, the islands are formed like droplets as the material comes to the surface. So these areas to the west are no longer active. The activity is down here in the southeast. So that's called a hot spot. And there you see Hawaii, Kilauea. I haven't heard much of the news in the last few weeks, but evidently it's still erupting in Hawaii. And so I thought I'd illustrate it here. So here comes the stuff to the surface, and there goes the plate moving off to the west. And so today the big island of Hawaii is being formed, and there's an offshore volcano, underwater volcano, known as Loihi. And so this whole area is active. Mauna Loa, Mauna Kea, not so much in the last couple of years. Kilauea, which is the most active right now, and the continuous eruption offshore here. And if it continues, and there's no reason to think it would not continue, then we'll have the next of the Hawaiian Islands off here off the coast. So you can go to your realtor and start buying property, and you'll have some Hawaiian land. So that's called a hotspot. Hotspots occur in many other parts of the world. I'll come back and mention some, but let me just finish talking about islands. Another category of island are these atolls, and here's a typical one. Very shallow, close to the sea level, and usually enclosing a lagoon. And this one is completely enclosed. A lot of them don't make the full enclosure. But going all the way back to Charles Darwin, he figured out how these things were formed. These islands are limestone, and they're formed from coral deposits. Now, coral is an animal, and it grows and it leaves behind, of course, the hard coral shells. They're formed around volcanoes. What happens is the coral will grow at the base of one of these volcanic islands. As I mentioned, Charles Darwin was the first to describe this. And then as erosion wears the island down, assuming that the eruption stops, and eventually the volcano's gone, but the coral stays. And the coral continues to grow, to build on itself. And so you have the persistence of the island in an area where the volcano gave origin to it, but the volcano has long since disappeared and is not within the picture anymore. So, and I think it's interesting that Charles Darwin described it first, and it's been elaborated on more recently by many others. Back to hotspots for a minute. Here's another one. This is called the Louisville Seamount Chain, and you see its relationship to New Zealand and Australia. I forget which end is active. No, I'm sorry. This is yeah, which end it is. But this is similar to the Hawaiian Islands, being formed by emergence at one spot. There's some here in North America. Here's one up in Canada, and it's called the Anaheim Volcanic Belt. All of these volcanoes were formed at a hot spot here, and the North American plate has been slowly moving off to the west. So each one of these volcanic features is a result of that. The most famous of these is Yellowstone. Yellowstone is a hot spot. And all of the activity in the Yellowstone Park, the geysers, the mud, the bubbling mud lakes, and all of that stuff is the result of volcanic material beneath the surface. You have hot stuff down below the ground that's active, and so you have this magma chamber down here. And as water circulates down below the surface and it comes in contact with this heat and then turns into steam and blows back to the surface, Yellowstone Park itself is a large caldera. And a caldera is just a big volcanic feature. It's essentially where you had a volcano and the whole volcano is collapsed into one big circular, it's not a crater, it's much larger than a crater. And so here you can see the outline of it. And it's continuously being monitored. It's active underground. Earthquakes occur periodically. They measure lake levels here in the lake, Yellowstone Lake, and at times it's the lake level is higher in the south, sometimes in the north, and so there's a good bit of disturbance here within this area. And as I mentioned, this is a volcanic hotspot. Here's an image of the earthquakes in the park since 1973 up to 2012. Stars are the big earthquakes, but all the little red ones are events, or earthquake events that have occurred here in this region. So it's still very much active. If you go southwest of Yellowstone, you see the continuing evidence of that hot spot. So if you've traveled much within this area of Idaho, and on further down to the southwest, you run across these volcanic areas, these areas of lava fields. And all of this is evidence of volcanic eruptions that happened up here where Yellowstone is, but are evidenced on the plate, the North American plate that's been moving off to the southwest. And so here you can see, for example, this one 13 million years ago, more recently 10 million years, 6 million years. And they estimate that the period of these eruptions is about 600,000 years. That's how frequently they occur. And the last eruption was 640,000 years ago. So if the average period is 600,000 years, then we're due for another one. And it would be a major catastrophe. We worry about Hurricane Michael and other features, but this would be something that we have never seen anything like. My daughter lives in Montana. She would not survive. So anyway, that's it's what's referred to as a supervolcano. When it erupts, it just really blows up and creates major destruction. So let's hope it doesn't happen anytime soon. Okay, well, to summarize plate tectonics, this idea of drifting continents, motion of the plates, contact point between plates, evidence of the alpine features, all of this then has answered many, many questions. As I mentioned last time, it's the most comprehensive model to be proposed within the earth sciences, certainly in the last century. And we are still trying to understand the process, what's going on. As I mentioned, many lingering questions. How long has it been going on? Well, since the beginning of the planet, don't know for sure. Do the same continents continuously come together and then spread apart? Some of the fragments do, but to what extent are the continents ground up and folded down into the interior of the earth? Don't know that. The main thing is, why does it happen? What's going on? Does it have to do with characteristics of the core? You know, there's some instability within the core of the earth. Gravity, the moon, they are still trying to piece all of that together and come up with some answers. So if you know any of those answers, let me know. All right, we'll talk a little bit about the oceans and then move on to something else, to a few concluding remarks. Unfortunately, we don't have time in a course like this to do justice to the sea. The oceans make up most of the Earth's surface. I'll let the planet spin here for a little bit. And just notice how much of it is blue. Greatest percentage, at least half of the planet, all of one side, the Pacific Ocean, is covered with water. And then the oceans continue and are continuous throughout the world. And as I mentioned at the beginning of the course, 71% of the surface is water. And we're talking about the salt water. So even though we focused on the land areas, the water makes up the majority of the surface of the planet. Some more evidence of this is a map like this. I thought this would be interesting to you. If you were to drill a hole straight down through the earth from somewhere, from anywhere, what you see is what you would find. So if you look at just the blue, for example, the blue continents, and you were to drill straight down anywhere within these continents, the fact that it's blue means that you would, on the other side, directly opposite, you would hit water. You would come up in the ocean. That's called the antipode, by the way, the other side. Only in a few areas would you hit land. So if you drill straight down, let's say here in Paraguay, you would come up in China. My mother used to tell me, well, if you go through the earth, you'd come up in China. Well, you won't. Would end up in the ocean. We wouldn't even hit Australia. See, it's out in the middle of the Atlantic. And so only here would you end up in, and that's about, except for some of the polar areas, I guess. That's really about the only major area where you have this. And so that indicates how much of the Earth's surface is covered by water, most of it. And talked about all of these ocean areas. They're all interconnected. They're all interlinked. And we have done a lot to map the sea floor. So we know where the deep areas, we know where the trenches are, we know where the shallower regions, these underwater mountain ranges that we've been talking about. And also here you get really good evidence of the continental shelf, all of the orange areas. So the continental fragments, even though normally we look at the Earth and look at the outline of the continents by looking at the seacoast, really we probably should be looking at the edge of the continents. There's a shallow portion of the continents that extends out under the water before it drops off to the depths of the sea. And so this continental shelf then is really part of the continental fragments that we've been talking about in the context of the ancient continents. You have the continental shelf, and then the slope, and then eventually you're off into the abyssal plain, as it's referred to, with an occasional trench, underwater canyon, associated then with this subduction of the various plates. And we talked about that, a lot of igneous material on the floor of the ocean. Very good course that Don Baker taught a couple of times ago, a couple of terms ago, is by this fella, Harold Tobin. And if you can get your hands on it, I would recommend it. Talks all about the oceans and oceanography. So what would you study in a course about the oceans, oceanography? Well, climate and the seas, coastal science, hazards, chemistries, all kinds of things. Don's teaching one on life in the seas, which would be covered, resources. And so there's a lot to be talked about when it comes to looking at the oceans. And any one of these then could be a full course. I'll mention a couple of things related to the seas. One is movement and the circulation. Of course, wave action is important. And you can have small waves or bigger waves. And this is some concern because waves can be, when they get very large, can be catastrophic. This was the tsunami event that hit Japan a few years ago. Remember, affected the nuclear plant at Fukushima. Anyway, these massive waves caused by earthquakes. So under certain conditions, earthquakes can create what appear to be minor disturbances out some distance from land, but as the water moves towards shore, the increasing shallowness or decreasing depth tends to focus that wave action, and you get these catastrophic events, killing many people. Another thing that happens is periodically out in the ocean, you have what are referred to as rogue waves, just very large waves that will destroy ships. On average, 2 big ships sink every week. There's a website that catalogs these things, and we're talking about big freighters and tankers and things. And many of them, as a result of these unexpected waves, simply out in the middle of the ocean, not associated with any particular storm or anything else. And there's an interesting book by Susan Casey called The Wave, and she talks about a lot of this. Well, how does this happen? Well, you can get patterns of waves. And in some cases, the patterns of the wave action are sympathetic. And in some cases, the randomness of the wave, they're not going to create any problems. But in certain circumstances, if you get multiple patterns where there is some coincidence, where there's some interference that turns out to be what they call constructive interference, as I've illustrated here, where you have the two crests and the troughs being associated, well, they can magnify each other. And you get a few of these together, and it can create massive, gigantic waves as opposed to destructive interference, where the waves are, the pattern then is in opposition to each other. And they've modeled all of this. I thought I'd show you a cute model. And so you can see these bumps then are where you're getting the constructive interference, where the two waves come together, and so it doubles the size of the original wave. You can try to harness the waves to generate electricity, and they've done this in various locations. I'm trying to remember that. This might have been in Portugal. Anyway, there are several places where they have proven the concept, but it's not yet been developed on a large commercial scale. Still working on that. Another thing related to movement of the sea are tides. As you know, tides are caused by the moon. If you've ever been to the Bay of Fundy, you know that's a area where the effect of the tides is shown dramatically. So you can walk out and you can walk out here and look at all of this stuff, and then they blow a horn, and you better run because the water's coming in, and it comes in fairly rapidly, and you don't want to get caught out there when it's coming in. And they've talked about using this tidal action again to generate electricity. The motion back and forth of the water can be used, can be harnessed. You can harness the energy and then use it commercially. Tides are caused by the moon, and when the moon, here's the moon over here, and the sun are aligned, then you have a fairly significant tide. It's called a spring tide. Sometimes they are at 90 degrees to each other, and so in this case, the sun is pulling against the moon and is not adding to it. These are referred to as neap tides. So both you have big high tides and smaller high tides, but again, all caused by the gravity action of the moon. And the moon will also deform the land. We don't perceive it, but as the moon goes around, the gravity does disturb the land itself. Well, how about currents? Here's a diagram, and you can go on the computer, on the internet, and they will show all of this stuff in motion in there. It's really quite dramatic. But here are major currents around the southern tip of Italy. And so you can see the flow of the water, generally various gyres, these circulations around themselves, and the prevailing currents flowing here between Sicily and Africa. Major currents of the world are driven by the wind. And so if you recall some of the wind patterns that we've talked about, you can see some correspondence with the currents. Okay, well, here's a diagram when we were looking at climate I used. Notice the prevailing trade winds out of the northeast, out of the southeast, the Hadley circulation, all of these currents at the equator going from east to west. The winds going from east to west, and then the wind flowing back in the opposite direction as you move toward the poles. Well, if you look at the currents reflect that wind pattern. So here you have the western drift, this cold current moving from west to east, again driven by the wind, and then driven by the wind in the equatorial region from east to west. But it's a little more complicated than that, because the wind at the surface drives a current, but as you move further down in the water column beneath the sea, the rotation of the earth, the Coriolis effect, starts to kick in. And so you get more complicated patterns down at deeper levels. And without going into all the detail, this is referred to, you can look up Ekman transport, and it will sort of explain as to how all of that happens. But basically at the surface currents primarily driven by the wind blowing the water. And here you can see the prevailing current patterns in the Atlantic Ocean. So when Columbus sailed off to the New World, he sailed south not only to pick up the wind, but also prevailing currents that would push the boat from east to west. And then the Spanish fleet going back to Europe would always travel along the coast of North America, follow the Gulf Stream and the wind patterns back to Europe. The Gulf Stream is a warm current coming up from the Gulf of Mexico, and up here and off the coast of North America then begins to interact with the cold water. Red here would be hot, purple and blue colder. There's an intimate connection between the ocean and the atmosphere. One illustration of this is the El Nino effect that periodically occurs. Just show you a time lapse of water temperature. And you can see the cycling of the seasons, the advance of the ice, polar ice, and then the retreat. But notice this area along the equator. Look at the hot water. And notice in this region off the coast of South America, you have prevailing fairly cool water in this area, warmer up to the north. But every once in a while, and we'll see when it happens, this area will become much redder, become much warmer. And these events are referred to as El Nino events. This whole area becomes, the water gets much hotter. Let's see, I think there's one coming up here in a couple of years. So here, that's pretty warm right now. Notice this would be an El Nino event right here. El Nino is called El Nino because it often happens around Christmas time, and so it's in reference to the birth of Jesus. Effects, we're more aware of the effect up here in the United States, usually creates very severe storms off the coast of California. And it's a periodic event. In Peru, it's devastating. Massive flooding. Coastal Peru is basically a dry region. And when you have a lot of rain in what are normally desert areas, it really creates havoc because construction is not designed to withstand a lot of torrential water. A lot of these streams that flow down to the coast become engorged, so you have massive flooding. It's very disruptive. The fish go away, so the fishing industry comes to a halt. And it's all related to changes in what's referred to as a thermocline. Thermocline is the area within the depths of the ocean that separate warm water near the surface from the much colder water down below. And it's an area, it's a transition area, a very dramatic, rapid transition in temperature. Basically what happens in the Pacific Ocean is that warm water invades areas here. Well, this is a normal situation. The area along the coast of South America is normally cold water. You have a bunching up of hot water over here in the western Pacific. But for some reason, that area of hot water and that bulge of water drifts back to the east. And it changes this thermocline. It becomes much more level. So it's almost like having a pot and sloshing the water back and forth, driven by the changes in the high and the low pressure in the atmosphere. And it happens on a fairly regular basis. And the opposite event is called La Nina. And so you have El Nino and La Nina. And they are still trying to understand why this occurs. You know, this periodic event, this cycling back and forth of the water sloshing around in the Pacific. Nevertheless, it is important because it gives us evidence of the interaction between the atmosphere and the sea, and of course it's disruptive to the people who live in some of these areas. Okay, yes.
What are the characteristics of
La Nina would be just the opposite. That means you would have increased cold water, much calmer, dry conditions off the coast of California, much greater stability. Meanwhile, much stormier off the coast of China, that part of the Pacific. Okay, I tell you what, let's take a quick break. I'll come back and talk about this a little bit, and then we'll move on to something else. Quick break, 5 minutes. Carolyn just told me that Helen Brown has been in the hospital. She's sort of a fixture at Auburn, at Ollie, and is going to be moved to Phoenix City. So keep her in your thoughts. All right. Let's talk about this thermohaline circulation here briefly, sometimes referred to as a conveyor belt. Talking about movement of the water, there is a deep current, or at least a portion of it is deep, that flows around the planet. And some of it is warm, some of it is cool, moves slowly, but here you can see the basic outline, the basic pattern of how the water goes. And what happens here is that at the poles, generally in this area, this is where it happens most to the greatest extent, because of the freezing of the ocean, the ice doesn't take up the salt. The ice is essentially salt-free, and so all the salt, when that freezing occurs, stays in the water. So the water here, salty water, is denser, and so that cold, salty water will sink, will go down. And as it goes down, it's replaced by warmer water coming up from the south. So the water density increases with salinity and the heavy water sinks. And essentially that sets up a circulation motion of the water, and you can see the general outline of it. Here's a more complicated picture. There's a current that surrounds Antarctica, and it gets fairly complicated. Yes? Colder water is denser, yes. Oh, I didn't realize that. So that's different for the different oceans? Yeah. Okay, great. Well, I'll pass it on to the rest of you.
Colder water is less dense. That's why ice floats. At about 3.5 degrees Celsius is where the temperature or the density versions occur.
Well, I'll defer to the experts. I know the salinity is what makes it sink. That's what makes it sink. Takes thousands of years to complete a cycle here. Now, I don't know how they tag the water and know where it is, but anyway. And here you see some more of it. One thing that's come up is a lot of talk about global warming and climate change. That's one of the concerns, is that changes in the characteristics of the ice up here in this polar region, melting of the Greenland ice sheet and changing in the icebergs and so on, is going to change this circulation, and it will interrupt this whole conveyor belt. And we really don't know what the long-term consequences of that are going to be. Assume that it'll be significant, but we don't know exactly what might be the result of all of that. Some evidence that it's already happening, and I'll show you a couple more of these here. This is deviation from what you might call normal. Normal here would be the period from 50s into the 80s, and then more recently. All the red shows that we've gotten warmer. This is hotter. But there are a few spots where the temperature has been cooler of North America and this area of the North Atlantic. Notice this blue area of the North Atlantic, so it's possible that that is already indicating some sort of interruption or at least reduced flow in this ocean circulation, this conveyor belt circulation. We'll wait and see how that turns out. Here's a more recent one, not as dramatic, but nevertheless still there. Okay, talk about resources in the ocean, the fish and the animals. Took this picture in Manta, Ecuador. We were looking over the ship, and they're just trawler after trawler coming in with, these are tuna fish, and they're frozen. They catch them and they freeze them, and then here they're being offloaded, getting ready to be shipped off for processing. And when they started doing it, there was a guy down in the bottom of the truck here, and evidently he got out. This is an area known as the Mississippi Dead Zone. This is where nothing lives, again, because of all the runoff. And I'm assuming some of you are fishermen that this is true. A lot of oil exploration, exploitation, major resource in the oceans, major oil wells, again, down along the Gulf Coast. You can see all these platforms. Of course, a few years ago, we were affected by this disaster. Unfortunately, they got it capped off. Okay, I want to talk a little bit about just some general things about planet Earth. There's much more we could talk about the oceans, obviously, but that was just kind of scratching the surface. It's a beautiful place. Don't need to tell you how important it is. Full of life, plant life, animal life, and of course our life. And so it would pay us to be aware that this is where we live, and we need to take care of it. We're not the only life, of course. Life has managed to establish itself in the most inhospitable areas, polar regions, plains, life, all kinds of life. We have made our presence felt along rivers. This is Rotterdam in the Netherlands, India, of course. We make use of polar environments for entertainment, enjoyment. We go into the deserts and dig up mineral deposits. I think this is, I'm not sure which mine this is. This might be Chuquicamata down in Chile. And of course, we depend on the planet, we depend on the earth to sustain us. We grow our food and harvest it, and that's how we survive. So it's imperative to take care of the planet. There's an intimate relationship between people and the physical environment. We've recognized that for a long time. It's been very, very important. And it's a two-way street. We are dependent upon the planet. It influences us. I'm talking about the physical geography, the oceans, the landscape, all the features, but in turn we affect that physical geography as well. So we can talk about how the physical and the human are connected. We adapt to the physical world. And it's not by accident that you live in housing made of ice and you don't have a lot of window space and sunroofs or anything like that. I got a kick out of that one. Not sure that's a real igloo. And of course, even in the driest of deserts, we managed to establish ourselves. If there is some presence of water, then we can make use of it. House types vary from one place to another. This would indicate a fairly cold climate. Notice the steep roof dictated by the presence of snowfall. And some windows, but windows fairly small, again, to keep the harsh winter from coming into the house. Ellen Churchill Semple and Ellsworth Huntington, back over 100 years ago, had some ideas about the relationship between people and the physical environment. And they were what you might call founders of a movement that was known as environmental determinism. And Semple in particular was a good writer. She had a flowery way of describing things. And she said that, well, the physical environment produces us. Everything about us, everything, whatever we think we are, it is a result of our association with the physical environment. Physical environment determines the way humans are. And she had various examples. She said people in the Mediterranean had big shoulders and muscles because they would go down to the sea and go catch fish. Now, I'm not sure that connection is valid, but anyway, she said it. She said people in Africa were good at running because they had to flee the lions. Well, that may have been true, but I'm not sure that is. But anyway, she described all of that. And so physical characteristics of the human body reflected the nature of the natural environment in which these people lived. And they would go on, and I'll just run through a quick example of the kinds of things they would say. If you look at the earth and look at economically developed areas, now we're talking about late 19th century, these are the areas that would have been pointed out. North America, Western Europe, probably Southern Australia and Argentina. Argentina at that time was a thriving country. And somewhat reflected today, although not exactly, but the more developed areas are within these regions. Well, they said, the environmental determinists, Huntington in this case, said, well, we got it figured out. We know why economic development occurs. It's a result of climate. It's obvious. If you look at temperature, all of those areas occur in temperate latitudes, temperate areas. None of those areas are found in the hot tropics. And so they would go in and they would rationalize and say that, well, in the tropics, people are lazy. You know, that's because nature is so bountiful. If you want food, you just go out and sit under a coconut tree and it falls in your lap. Or, you know, if you don't want to work, you don't have, just take a siesta. Life is easy for you. Meanwhile, people living in the temperate zones and the colder climate, it forces folks to be more industrious. And so you work harder. It stimulates the blood flow and you feel more energetic. But more than that, because you have to face a non-productive winter season, then you have to produce in the summer and save up and invest in the future. Remember the fable of the ant and the grasshopper? Well, the dumb grasshopper just played around and fiddled away while the ant was putting away food. And so the argument goes that, well, in these climates, people learn to invest, learn to think of the future, so you go to college, so you get a good job. All of those kinds of things make people who live in temperate regions more productive. Well, without getting into a whole lot of discussion, hopefully you realize that that sort of argument will break down. If that were the case, most productive people in the world would be let's say, the Eskimos who live in the North Pole, where the climate is harshest. If anything, tropical climates are harsher than temperate climates. If you look at food production, if you look at other characteristics, pest infestations, all of these things are more problematic in tropical areas than they are in temperate regions. And so some of it breaks down. But that's the kind of argument that would be used to justify these sorts of connections between physical geography and human activity or human conditions. What we know is that physical geography and the Earth itself influence us in many ways, but you cannot take the extra step and talk about determinism. That's not the case. Well, I'll send that to you. It's a quote from Adam Smith. So you look at the way the people are dressed. Well, climate obviously has an impact, influences, or where you get your food. You know, living in the desert, you're not going to grow coconuts. You're going to raise goats because that's something that will sustain you in that sort of environment. Another example, we've been talking about the fall line. Well, if you look at major cities in the southeast, they are often associated with the fall line. So there's a connection there. Rivers flowing over waterfalls can be used to generate electricity. And so these become areas of settlement. It's also a place where if you're traveling by boat, let's say up the Savannah River, how far up the river do you go? Well, you get as far as Augusta, where the falls were, and then you have to get out of the boat, transship around the falls, and go on upstream. Well, so these areas developed early on as major cities in the southeast, from Montgomery, Columbus, Macon, Columbia, South Carolina. And so there's a connection there between settlement and the physical geography, although not deterministic. On the other hand, the flip side of the coin is we have impacted our natural environment. If you look at Alabama, native forests, this is what the forests look like today in Alabama, mostly pine trees. The Everglades down in South Florida, this is South Florida today. So we modify the physical environment. Plant corn all over the Midwest, desert Southwest. Sometimes things go wrong. And could give you, we could all think of many examples of this sort of thing. A lot of concern about the Pacific Gyre, where we have all of this hundreds of square miles of plastic drifting around and trying to collect it. Of course, this illustrates the consequence of all of this. Talk about climate change a little bit. I know within here there's at least one non-believer, but I happen to believe that this is something of significant concern. A lot of evidence that the climate is warming up. Glaciers around the planet are withdrawing, backing. The ice sheet on the large island of Greenland is melting. If you look at the snows of Kilimanjaro, Hemingway would have had to retitle his book. The snows are rapidly retreating and they'll be gone within a couple of decades. Snow cover greatly reduced. This, without all the details, this is the reduction in snow cover over the last couple of decades. We can go back and look at temperature anomalies, slight decrease, but in the last few decades, dramatic increases in temperature around the world. More evidence of this. Running 5-year averages and some difference between the northern and southern hemisphere. Northern hemisphere is more land-based, and so it's to be expected that change would be more dramatic. This is comparing the 2013-2017 average to an average between 1951 and 1980, using that as a baseline. And you can see, by and large, the whole planet, especially the northern hemisphere, is getting much, much warmer. Each year, we set a record for overall climate temperature. Sea level rising. A lot of evidence of this. Here are estimates of past sea levels, and you can see projections into the future. Now, It's not going to affect us here in Alabama so much, but in other parts of the world, it will have an impact. We were in Miami a year or two ago, 2 years ago, and they are reconstructing some of their streets down there in anticipation of rising sea level in Miami Beach. Big impact in places like Bangladesh would be very disruptive. Why is it happening? Well, there are all kinds of models. Main model has to do with basically the greenhouse effect, release of carbon dioxide, carbon monoxide into the atmosphere, traps the heat, stores up energy within the atmosphere, and so a lot of the energy that used to radiate as long-wave radiation back into space now becomes trapped from the light strikes the earth and gets trapped into the atmosphere, and so the atmosphere then is acting as essentially a blanket that's warming up the planet. I said the models are pretty complicated, so there's one of them. Why is that happening? Here is what is a little more controversial. Most people that I read at least say that it's because of human activity, primarily consuming fossil fuels, not only transportation but also power plants. I mentioned the greenhouse model trapping the energy. Here is evidence of the concentrations of these greenhouse gases. You see great increases, carbon dioxide, methane, in the atmosphere. And so there's a lockstep increase in these gases along with the increasing temperature. What's causing it? Well, primarily electricity generating plants. We talk a lot about electric cars and all of that. Well, if you think about it, electric cars are not going to be the final solution, because if we have to generate a whole bunch of electricity to run these vehicles, then we're kind of back where we started. Better fuel consumption zone, that will be a help. Where is it happening? Well, here you can see 1990, 2014, United States, our percentage has actually been reduced, as has Europe. Big increase in China, however, and even Russia's gone down. So the balance is changing, but we're still releasing a lot of this stuff. Consequences, well, they think that a lot of the coral around the planet are dying because of increased temperature, also probably because of growing acidity in the oceans. Changes in temperature, just run through some of this. Melting of the polar ice caps will impact the polar bears dramatically because they depend on that ice cover. But positive consequence is trade will probably open up on this Northwest Passage, because it is now pretty much free of ice throughout the year. Bad consequences in certain areas. The Maldives or islands south of India, they will be completely underwater. All of that. Here, they had a cabinet meeting over there to illustrate, to draw attention to the fact that they're going to have problems. New York City, increased severity in storms. We may be seeing some effect of this already. I am pretty well convinced that the increasing fire presence in California, of course, that's a function of overbuilding. So, we're concerned about the destruction of property. But the fact is that California seems to be getting hotter and drier, which might be a consequence of some of these changes. Talked about that circulation may be affected. Reduced plant and animal diversity. Some estimate that the number of species on the planet within a few decades will be cut in half. Total variety will cause massive relocations, dislocations. Bangladesh will suffer. It's a country with high population densities. All of these areas are going to be, the red areas are going to be severely affected, not only by encroachment of the sea level or rising sea level, but also the penetration of salt water. And so basically it's an agricultural country, and so these areas will become brackish and saline, which means they'll be unsuitable for agriculture. So that could be a major disruption. What can we do? Probably can't stop it. It's too far gone. Can mitigate it, adapt, and here's my recommendation: buy a land in Canada. Because there'll be areas that formerly were not inhabitable, but or Alaska, I guess. So why concern about all of this? Well, we depend on the physical environment for our survival as a species. If we're going to survive, we need to be careful. Just to finish off with some pictures, contrasting scenes, some negative. Although if you own some of that property and you're getting wealthy, that's probably not negative at all. Again, overcrowded, congestion. I was going to say something about some of these authors, but we don't have time. Big area in geography is what they call cultural ecology, and that's the careful analysis now of the interrelationship between people and the physical environment. And we're not deterministic anymore, but we don't ignore that relationship, how interdependent we are on our physical environment. Very important to us. Basically, we live in a constructed world, and we need to maximize our preservation and our concern for the planet that we live on. Okay, next course, maybe next fall, I'm going to talk about human geography, so we'll come back and get into some of these sorts of things. We have a few minutes, and I ended a little early on purpose to see if you have any comments or any questions, things. Yeah, John?
Back on the earthquakes, what you said earlier,
Yeah.
our area that we're in here is a low area for earthquakes, and not the lowest.
That's right.
Yeah, do you think we should get earthquake insurance?
Well, that's, that gets into economics. And, to sort of be serious about something that, you may have intended to be facetious, it's all about trade-offs. The people on the Gulf Coast, do they need to buy insurance for a hurricane that's going to show up every 50 years? Or, it's a matter. Personally, I don't think we're in any danger here of experiencing a major earthquake. We've experienced some minor ones. In fact, I remember several years ago, Barbara and I were sleeping in bed, and I felt I felt her wiggle around, and lo and behold, we were experiencing an earthquake. It wasn't a truck or anything else. There was a major earthquake up in the vicinity of Washington, D.C. Was it last year or sometime recently? And kind of destroyed some buildings and things. So they do happen. Now, some of the shield areas, so Central Australia, Northern Canada, Eastern Brazil, I can just about guarantee they'll never experience an earthquake. But where we are, now and again. Yeah, Jim? I remember reading in the paper, it was last year, maybe a couple of years ago, there was an earthquake of some significance up in Northern Virginia in that area. Oh, I like that one. I remember that. Yeah, Mike.
I'd like to reflect on what statement you made earlier about whether cotton is blooming or not.
Yeah.
The average age of continental crust is almost 1 billion years old. Yet the oldest age for oceanic crust is only 70 days.
Mm-hmm.
So all of the oceanic crust was recycled in 70 billion years, and we don't know how long it takes to recycle continental crust, because here even in North America, the continental crust is over 1 billion years old.
That's right. And I used the illustration of a few sessions back. Remember the kids floating in the swimming pool? That's sort of like the continents. They bump into each other, but a lot of that stuff doesn't get folded down. The rocks are lighter, and so it just kind of stays at the surface. Bobbing up, yeah. Yeah. Well, and it's not the only salt lake. There are many areas around the world. What happens is you have a significant amount of water. You have runoff of materials from surrounding hills with a lot of salt. And over the years, since those bodies, not only the Salt Lake in Utah, but other ones, there's no outlet to the sea. As evaporation takes place, all of that runoff, the salt doesn't go away. The salt doesn't evaporate. The salt stays behind. So you have higher and higher and higher concentrations of salt in the existing water that's there. And so it's because of that lack of interaction with anything. You know, the water that runs into the lake is just saturated with these minerals, this salty minerals. There are other areas, you know, there are areas in South America, the Great Salt Flats of Uyuni in Bolivia, areas in Central, that's what's happened to the Aral Sea as well. Okay, no more comments? You're welcome. Thank you. You all have a good break, and we'll see you in the wintertime.